Subcommittee on Energy will come to order. Without objection, the chair is authorized to declare recesses of the subcommittee at any time. Welcome to today's hearing entitled Nuclear Energy Innovation and the National Labs. I now recognize myself for 5 minutes for an opening statement. Good morning, and I've already welcomed you to the committee hearing this morning. We appreciate you all being here. Today's hearing will focus on the Department of Energy's National Laboratories research capabilities and the working relationship with the private sector to advance nuclear energy technology, both fission and fusion. The Department of Energy owns 17 national laboratories, 16 of which are operated by contractors as federally funded research and development centers. The government-owned, contractor-operated model allows the labs flexibility to think outside of the box when tackling fundamental scientific challenges. The Department of Energy labs grew out of the Manhattan Project and today provide the critical R&D infrastructure that will enable researchers in academia and the private sector to develop the technologies of tomorrow. It's pretty clear that the challenges in nuclear science can be quite complicated, and we'll hear more about that from our expert witnesses on our panel today. That said, not being a nuclear physicist or anything of that sort, I'm going to do my best to simplify what we intend to discuss in today's hearing. We hope to get a better understanding of what the DO labs do and how their unique research machines and talented group of researchers can enable companies to develop new products. This is especially relevant for nuclear energy R&D, which requires large upfront costs, but may lead to revolutionary technology with long-term rewards. Folks, I would add that the United States has a definite national interest in maintaining our position at the forefront of nuclear technology development. Nuclear energy, as you know, is in a class of its own with the highest energy density of any fuel and yet yields zero emissions, the big goose egg. It is also highly regulated, often a centerpiece of global, especially national politics, and it's associated with the world's strongest economies. In the United States, we invented this technology and cannot forego, we must not forego the opportunity to export more efficient and safer reactor systems that will mitigate proliferation concerns while increasing global stability by providing a reliable energy source. Today we're going to hear from the president of a charitable organization that has co-invested with the DOE lab to advance a specific nuclear fuel treatment process to convert nuclear waste into a usable fuel. We will also hear from the Oregon National Lab, which invented this fuel treatment process, as well as private companies developing fusion and advanced fission reactors. Needless to say, this is a unique panel of witnesses. I thank the witnesses for participating in today's hearing, and I look forward to their testimony. Mr. Grace from Florida, you're recognized for 5 minutes.
Thank you, Chairman Weber, and for holding this hearing, and thank you to our witnesses for agreeing to participate this morning. For decades, the federal government has provided critical support for energy research and development. From solar to wind energy to natural gas recovery, many of the technologies allowing us to transition toward a clean energy economy and creating entire new industries would not be possible without federal support. And the same is true for nuclear energy. This morning, we will listen to you all regarding the federal role in developing the next generation of nuclear energy technologies. I'm particularly pleased that as part of this discussion, we will learn more about innovative future fusion energy concepts that have the potential to accelerate the development and deployment of commercial fusion reactors dramatically. Fusion holds the promise of providing a practically limitless supply of clean energy to the world. In a sense, we're already dependent upon it because the energy that we get from that fusion reactor called the sun in the sky is essential to the existence of life on Earth. It's proving difficult for people to replicate what the stars are able to do through sheer gravity. But based upon several developments in recent years that we'll be hearing about in part today, I'm confident that we'll get there. And I hope far sooner than people may realize. I do have my reservations about fission, another subject that we'll be discussing today. Not about the physical process itself, but the applicability of that to our energy needs. I have described fission in a sense as a failed technology. There is a problem with spent fuel that doesn't seem to have a solution after many decades of consideration. We've had 3 nuclear disasters worldwide. But the answer to that may not be the German solution of simply scrapping. The answer to that may be to do further research and try to find solutions to these problems. In any event, I'm a strong supporter of fusion energy research, which is entirely different in terms of its impact and potential problems than fission. I believe that now is the time to build and operate experiments that are capable of demonstrating that man-made fusion systems can consistently produce far more energy than it takes to fuel them. I'm eager to learn about both the costs and the benefits of a wide range of new nuclear technologies, and I also look forward to hearing how nuclear energy can play an important role in developing a modern, clean energy economy. Again, I want to thank you all, our witnesses, for providing your insights today. And I look forward to hearing from the chairman and working with the chairman on nuclear energy issues moving forward. Thank you. I yield back the remainder of my time.
I thank the gentleman from Florida, and now recognize the gentleman from Texas, the chairman of the full committee, Chairman Smith.
Thank you, Mr. Chairman. And today's hearing will examine opportunities for advances in nuclear fission and fusion energy technologies. We will hear from the Associate Laboratory Director at Argonne National Lab, the home of the world's first reactor to demonstrate a sustainable fission chain reaction. Argonne National Lab is responsible for foundational research and development in nuclear energy that has led to many operating reactors and reactor concepts that will be discussed today. These include the integral fast reactor and pyroprocessing. We will also hear from witnesses who represent private companies and a charitable organization, all of whom have invested in the development of advanced fission or fusion reactor designs. Nuclear energy provides reliable, zero-emission power. This technology represents one of the most promising areas for growth and innovation to increase economic prosperity and lower the cost of electricity over time. This will help keep the United States globally competitive. The Department of Energy's national laboratories provide vital opportunities for the private sector to invest in innovative energy technologies. This includes its open access user facilities, which are one-of-a-kind machines that allow researchers to investigate fundamental scientific questions. These facilities enable a wide array of researchers from academia, defense, and the private sector to develop new technologies without favoring one type of design. This represents a better approach than simply picking winners and losers through energy subsidies. DOE's labs also provide the fundamental research capabilities that lead to scientific publications or proprietary research. In this public-private partnership, private companies take on the risk for commercializing technology, while the government enables researchers to conduct specialized research that would not be possible without federal support. DOE's national labs keep America's best and brightest scientists working on groundbreaking research here in the United States instead of moving to research projects overseas. I am hopeful that today's hearing can demonstrate the importance of foundational research capabilities in the national labs that will lead to the next generation of nuclear energy technology. Inevitably, and I hope sooner rather than later, all Americans will benefit from this research. Mr. Chairman, before you go back, I just want to apologize to our witnesses. I have another subcommittee meeting of another committee that I need to go to briefly and then hope to return. So, but do look forward to reading and hearing what the witnesses have to say today.
Thank you, Mr. Chairman. Let me introduce our witnesses. Our Dr. Mark Peters, our first witness today, is the Associate Laboratory Director for Argonne National Laboratory's Energy and Global Security Directorate, which includes Argonne's programs in energy research and national security. Dr. Peters has worked with the national labs for 20 years. In addition, he serves as a senior advisor to the DOE on nuclear energy technologies and nuclear waste management. Dr. Peters received his bachelor's degree in geology from Auburn University and his PhD in geophysical sciences from the University of Chicago. Welcome, Dr. Peters. Our next witness is Mr. Frank Batten Jr., Chairman and CEO of Landmark Media Enterprises and President of the Landmark Foundation. The Landmark Foundation focuses its efforts on helping local education and human service organizations. Mr. Batten received his bachelor's degree in history from Dartmouth and his MBA from the University of Virginia. Welcome, Mr. Batten. Am I pronouncing that right? Our next witness is Mr. Nathan Gilliland, Chief Executive Officer of General Fusion. Before joining General Fusion, Mr. Gilliland served as an entrepreneur in residence with Kleiner, Perkins, Caulfield, and Byers, one of the world's largest venture capital firms. In addition, he was the president and co-founder of Harvest Power, a renewable energy company that turns organic waste into natural gas and electricity. Mr. Gilliland received his bachelor's degree in accounting from the University of California at Berkeley. Welcome, Mr. Gilliland. Our final witness today is Dr. John Parmentola, Senior Vice President of General Atomics Energy and Advanced Concepts Group. Dr. Parmentola oversees a team of nearly 475 from over 90 institutions worldwide who lead the way in international nuclear fusion and fission research and development. Before joining General Atomics, Dr. Parmentola served as Director of Research and Laboratory Management for the United States Army. In addition, he served as Science and Technology Advisor to the Chief Financial Officer of the Department of Energy. Dr. Parmentola received his bachelor's degree in physics from Polytechnic Institute of Brooklyn and his PhD in physics from MIT. Welcome, Dr. Parmentola. We're going to turn to our witnesses now, and y'all are recognized for 5 minutes. We'd ask that you keep your testimony to 5 minutes. Dr. Peters, we'll start with you.
Good morning. Thank you, Mr. Chairman. I'd like to thank Chairman Smith, Chairman Weber, Ranking Member Grayson, Congressman Lipinski, Congressman Hultgren, and the other distinguished members of the subcommittee for your invitation to testify here today on this important subject. My name is Mark Peters, and I am the Associate Laboratory Director for Energy and Global Security at Argonne National Laboratory. And Mr. Chairman, I've prepared a detailed written testimony that I would request be submitted for the record, and I'll summarize it here.
Okay, without objection.
The history of nuclear energy development in the U.S. is one of cooperation amongst the federal government, its DOE, national labs, universities, and industry. The breakthroughs and designs achieved by the scientists and engineers of the National Laboratory Complex, and Argonne in particular, inform and drive every nuclear reactor design in the world today. The U.S. continues to be the lead source of innovation globally for the current generation of light water reactors, or LWRs, and small modular reactors, or SMRs, as well as leading in regulatory process, independence, and rigor. But a 30-year hiatus in the construction of new U.S. reactor projects has impacted domestic production capacity, investment in technology and innovation, and the domestic supply chain. The country's leadership in global nuclear energy could be further compromised as the world begins to move beyond the current generation of nuclear reactors to new designs, known as advanced or Generation 4 reactors, that can address the future challenges of nuclear energy. Other countries are forging ahead with new reactors that, when coupled with advanced fuel cycles, can address long-running challenges with nuclear waste management, make significant gains in efficient use of fuel, and operate even more safely than current generation reactors, further addressing lingering public acceptance and confidence challenges. Without a commitment to advanced reactor technology development and demonstration in the U.S., our country runs the risk of defaulting on the return of 7 decades investment in nuclear S&T and infrastructure. That lead position has allowed the U.S. to become the recognized world leader of efforts to control nuclear proliferation, ensure the security of nuclear materials, and promote safe and secure operation of nuclear power plants. If the U.S. is to ensure its rightful place at the forefront of advanced nuclear energy systems, it will require a new commitment to the type of public-private partnership that led to the creation of our current fleet of light water reactors. Our national labs and universities continue to work closely with industry to accomplish much of the research necessary to facilitate advanced reactors, but substantial work remains. A new generation of advanced reactors will require refinement and demonstration of new technologies, as well as a test reactor and test bed for demonstration of advanced reactors. More work remains to be done on advanced fuel cycles and providing options to close the fuel cycle, decreasing the amount of waste that must be stored, and simplifying geologic disposal requirements. Perhaps no effort better illustrates how cooperation between national laboratories and industry can enable important breakthroughs in nuclear energy than the long-running collaboration between Argonne and General Electric, Hitachi Nuclear Energy. This collaboration stretches back to the 50s in the days when we were working on experimental boiling water reactors in collaboration with GE, and more recently in GE's advanced reactor design known as PRISM, which also has its root in this public-private partnership. And PRISM was created using principles demonstrated at Argonne's Experimental Breeder Reactor 2, or EBR2, and further refined in the Integral Fast Reactor, or IFR. With the creation of EBR2 and the follow-on design of IFR, the march towards continued U.S. leadership seemed inevitable. However, in the 1970s and 80s, a variety of developments coalesced to move the U.S. away from nuclear energy and next-generation reactors and closing the fuel cycle. Today, the severity of the need to fight rising levels of greenhouse gases in our atmosphere may once again drive the U.S. to regain its place at the forefront of nuclear technology. So our vast nuclear energy infrastructure, developed over decades with the combined capabilities of industry and the federal government, is at a crossroads, where existing nuclear reactors are set to be retired over the coming decades. While light water-cooled SMRs can serve as a bridge to the next generation of advanced reactors, many issues remain that can be addressed by advanced reactor technology. If we wish to chart our way forward towards those solutions, we must once again engage our public and private resources in a new effort to build the next generation of reactors. Much of the technology is developed and demonstrated on a small scale, although substantial work remains. The next logical step is to unify these technical efforts and successfully deploy a test reactor and test bed to demonstrate the advanced reactor systems. The time we have to demonstrate this technology is short due to the age of our current light water reactor fleet. Action over the short term is required to demonstrate new technologies by 2030, when retirement of existing nuclear power plants will accelerate. Thank you, and I look forward to answering any questions you might have.
Thank you, Dr. Peters. Mr. Batten, you're recognized.
Chairman Smith, Ranking Member Grayson, good morning. My name is Frank Batten, and I'm the president of the Landmark Foundation. We're a private foundation that supports educational, environmental, and human service organizations. I greatly appreciate the opportunity to testify today regarding a positive example of a near-completed Cooperative Research and Development Agreement, or CRADA. And we did this with the Department of Energy's Argonne National Lab. The CRADA relates to what we believe should be an important component of our country's national energy policy, which is the recycling of used nuclear fuel through a demonstrated U.S. technology called pyroprocessing. We have no commercial interest in this area and no financial agenda, but we believe that the U.S. can significantly benefit from recycling used nuclear fuel through pyroprocessing. While private industry can and should play a role, federal government R&D funds are essential if the benefits of this technology are to be realized. Pyroprocessing has been the subject of federal R&D for many years, and Argonne has led the way. The technology is now capable of recycling used fuel from the country's nuclear power plants for reuse to generate electricity in advanced reactors. Pyroprocessing is good energy policy, it's environmentally sound, it promotes effective use of resources, it can contribute to addressing climate change, and it holds the promise of significantly mitigating the country's used nuclear fuel disposition issue. I'd like to briefly summarize the success story of our partnership with Argonne, which relates to the design for a pilot reprocessing facility. I'd also like to brief the subcommittee on an analysis undertaken by Energy Resources International, or ERI. We commissioned and funded the ERI analysis outside of the CRADA. The ERI report analyzes the costs and benefits of using pyroprocessing and advanced reactors on a commercial scale. And I've attached a copy of the ERI report to my testimony and asked that it be included in the hearing record. The Landmark Foundation entered into the CRADA with Argonne over 2 years ago. We invested $5 million, and the federal government invested $1 million in the CRADA. The purpose of the CRADA is to develop the conceptual design and a robust cost estimate for a 100 metric ton per year pilot scale power processing demonstration facility. The CRADA is a particularly good use of the public-private partnership concept. It leverages prior government-funded work, it takes that work to the next level, and it builds a bridge for the U.S. government to move forward with the detailed design for the pilot facility. All of this, we hope, will spur additional federal funding for a pilot facility. The ERI report provides a detailed assessment of the costs and technical factors associated with a realistic fuel cycle using power processing and advanced reactors. ERI concluded that the potential exists to reduce the volume of used commercial fuel requiring permanent disposal by 50% or more, avoiding the need for a second geologic repository. Avoiding a second repository would save the U.S. government tens of billions of dollars. According to ERI, reuse of power processed fuel also would simplify the design of a first geologic repository and reduce the volume of repository space needed by more than 50%. This would significantly contribute to reducing the federal government's financial liability associated with its obligation to receive used fuel from its utility standard contract holders. I'm pleased to be here today to talk both about the success of our partnership with Argonne and the underlying benefits of further developing the power processing technology. Thank you for your time and attention.
Thank you, Mr. Batten. Mr. Gilliland, you're recognized.
Chairman Weber, Ranking Member Grayson, Chairman Smith, thank you very much for the opportunity to testify today about the emergence of new innovative fusion energy concepts and the importance of governmental support and working with U.S. labs. My name is Nathan Gilliland, Chief Executive Officer of General Fusion, one of the leading private fusion energy companies. I'll make 5 key points today and have done so in my written statement in more detail, which I'd like to submit to the record. First, as I would echo what Ranking Member Grayson said, the game-changing nature of fusion energy bears repeating. It's energy production that is safe, clean, and abundant. In a fusion reaction, 1 kilogram of hydrogen is equivalent to 10 million kilograms of coal. It's the energy density comment that you made earlier. Humanity would have abundant energy for millions of years. There's also no long-lived radioactive waste, no chance of meltdown in fusion reactions. The benefits to energy security can hardly be overstated. Second, U.S. support for magnetic fusion programs like ITER and inertial confinement programs like NIF have created an enormously beneficial source of research. ITER and NIF have justifiably been the highlights of the U.S. fusion energy framework and developed key insights into plasma behavior, material science, simulation codes, and many others. These programs should continue to be supported. Third, because of this historical research, innovation in alternative pathways to fusion have accelerated. These alternative approaches, both in private companies and in labs and universities, offer potentially faster and less expensive concepts. And demonstrable progress is being made, both in these labs, universities, and the private companies. Of particular note, work at Sandia, University of Washington, and Los Alamos are worth noting, as well as the 3 leading private companies, TriAlpha Energy, which is based in Southern California, Helion, which is based in Seattle, and ourselves, General Fusion. The progress of these alternative concepts was featured last summer in Science and Nature magazines. Novel fuels are being tested, new simulation tools developed, and we're all setting records of the stability of our plasma. So real progress is being made. Increased commercial viability, lower cost power, and faster progress are common threads in these alternative fusion concepts. Alternative approaches are reducing costs by applying existing industrial technologies to the challenge of fusion, primarily avoiding costly large lasers or costly superconducting magnets. Some have novel ways to protect the fusion reactor from neutrons. Others have simpler ways to convert heat into electricity. But of course, there are no silver bullets. These alternative approaches tend to be less researched and studied and are simply newer. The physics have not been fully explored. But we would argue the viability and efficacy of these alternative approaches can be demonstrated for less money. Some will show rapid progress and others will not. But dollar for dollar progress or failure can be demonstrated much more quickly. Fourth, though the majority of fusion research has been publicly funded, there is a place, and an important place, for private companies who can build on previous research and potentially innovate faster. The Human Genome Project is a great analog and a great example. The NIH built a core of research that was very strong, and from this, private industry was able to efficiently and rapidly innovate to sequence the genome. We see parallels in fusion energy. World-leading historical research is being done at labs and universities and has led to rapid innovation. And just like every energy industry, oil and gas, solar, wind, there will be multiple approaches that succeed in fusion. It's not a winner-take-all industry. Fifth and finally, going forward, we'd like to see more open innovation and information sharing across private industry, labs, and universities. For example, we all use computer simulation. It's a very important tool for us. We'd like to see co-development of simulation codes, more sharing of simulation codes. Another thing we'd like to see is greater emphasis on exchanges of physicists and PhDs across private industry and government labs. This leads to better sharing of historical research, current research, and the private sector would absolutely put resources into doing this. And labs and universities can help here at no cost to them. Ultimately, more cooperation between government-supported efforts and private industry can only accelerate progress. There is no value in silos. Let's push for more private-public partnerships, as Dr. Peters mentioned, and I'm sure Dr. Parmentola will as well. Let's push for more private-public partnerships to share data, build faster, and accelerate progress. The world needs fusion, and the faster the better. Thank you.
Thank you, Mr. Gilliland. Dr. Parmentola, you're recognized.
Good morning. Thank you, Chairman Weber, Ranking Member Grayson, and other members of the subcommittee for holding this hearing on this important subject. I believe, as many others do, that it is important to the future national security, energy security, and environmental quality of the United States that ample supplies of competitively priced nuclear energy are available. Unfortunately, it appears that nuclear energy is dying in the U.S. There are a few new plants being built. Several have closed recently, and most of the 99 existing plants will be closed down within the next 40 years. To place this in context, last year nuclear was 20% of the electricity consumed by Americans who paid $80 billion for it. We believe this death spiral can be avoided, but it will require active involvement by the U.S. government. The energy market is indicating that existing nuclear power technology is not commercially viable. For nuclear power to play any future role, the U.S. will need new, safer nuclear power technologies that will produce significantly cheaper electricity. However, the private sector will not be able to develop this on its own. The investments required are very large, they are risky, and in any event will take more than a decade before they might yield any revenue from electricity production, and even longer to yield any profit. As these new options are developed and private firms begin to see their way to risk reduction and making profits, private investment will increase, the government will be able to withdraw, and the market will decide which would be commercially viable. Let me now discuss GA's interest in a new advanced test reactor. We have a new reactor concept that needs a testing facility. We call it EM2. And we designed it to address the four most prominent concerns with nuclear power: its safety, its cost, its waste, and its proliferation risk. We believe it is a potential breakthrough technology for the United States. However, research is required to realize it. To develop EM2, a compact gas-cooled fast reactor, we looked at what physics indicates we must do. 1, we must go to higher power densities through a compact reactor core using fast neutrons. 2, we must go to higher temperatures, so a higher percentage of the heat produced is turned into electricity. By doing this, we can make the same amount of electricity in a smaller reactor, small enough that it could be made in a factory and shipped by truck to a site for deployment. We believe we could increase the efficiency of power production from percentages today in the low 30s to the lower 50s. The bottom line is, we believe that we could reduce the cost of electricity up to 40% below that of existing nuclear reactors and reduce their waste by up to 80%. But to do this, we have to develop new materials that will be able to endure the higher temperatures and endure the more energetic and neutron-rich radiation environment inside the reactor. We need a new testing facility with high performance characteristics in which to do this research work. But there are also a number of other companies and national labs that are advocating the use of fast neutrons and going to high temperatures, albeit with different advanced reactor designs. These also require a new testing facility that conduct tests in, say, 3 years that would show what happens to these materials in an actual advanced reactor during a period of 30 years. It would not make business sense for any company or even all interested companies together to pay for the capital costs to construct such a facility, given the large investment, the risks, and the very long lead times involved for return on investment. Currently, there is no U.S. facility with the requisite high-performance characteristics to do this type of research. The best we have are the Advanced Test Reactor at Idaho National Laboratory and the high-flux isotope reactor at Oak Ridge, but neither of these is appropriate for a number of reasons. The best in the world is in Russia, Bor 60, but this is being shut down soon for other reasons. In any event, it would seem odd to develop such a national security technology in Russia. Therefore, we suggest you consider building such a facility in the United States. It would be called the Versatile Advanced Test Reactor. It would be a highly neutron-rich, fast reactor capable also of producing thermal neutrons. We like versatile because it should be designed in such a way that it could be used to test all new reactor concepts, whether they involve molten salt, a liquid metal reactor, a liquid lead bismuth reactor, a gas reactor, or even light water reactor. The Versatile Advanced Test Reactor would be a user